That was the short version.
Thanks. Great. I'm excited to be up here in Jackson. This part of the country has a very special place to me, especially because I've worked a lot on the volcanic systems out here. So it's always nice to come back to a place that's so familiar and beautiful scenery. So today I'm going to talk about how we look at magma chambers.
I know you're a pacer, just so you know.
I know, I'm
Just,
sorry.
no, you're okay, but just so you know when you cross in front, you're gonna
Yes.
give up.
My head's going to get cut off? Okay.
close.
And I will try to not stand in front of the screen as well. So today I want to talk about how we
Do you want to sit?
look at, no, I definitely don't want to do that.
Okay.
She would never be able to sit and give a lecture.
How we look at the dynamics of magma chambers prior to eruptions of these super eruptions, and then last night I talked about the not so super eruptions. And so we're going to use microscopic zircon, which these are over here images of those zircon from the super eruptions to try to get at any relationship that might exist between the super and not so super eruptions. And I'll talk about those not so super ones briefly for those of you who weren't there last night. Mostly I work on the Huckleberry Ridge Tuff, which is the 2 million year old Yellowstone eruption, and the Mesa Falls Tuff, which is the about 1 million year old super eruption. And so I brought some samples with me today. If we have time, we can look at those afterwards. And these are pictures of the Mesa Falls Tuff and the pumices, and some of the ones that posed for this photo shoot are featured here as well. Okay, so let's start first with what's a super eruption, and I went through this last night as well. So super eruptions are defined by their size and how much material is erupted at a time. So the cutoff is about 300 cubic kilometers. And the Mesa Falls Tuff, the second of the Yellowstone super eruptions, actually isn't a super eruption because it comes in just a little short at 280. They are dominantly silicic systems, meaning that they are compositionally rhyolite. So you might hear the terms rhyolite or basalt. So these super eruptions are commonly rhyolitic eruptions, and they produce a lot of pumice. So I have some pumices up here for examples. They make widespread ash deposits that will reach as far away as the Gulf of Mexico. And sometimes they can even have global consequences. For instance, if Yellowstone was to go off, you can, right now it would bury the Midwest, which is, of course, where a lot of our crops are grown. So a lot of corn and things would be just completely obliterated. This image here is just showing the relative volumes of some of those. So this is the most recent Yellowstone eruption here, and then some smaller ones. This is let me see if I can do this. Mount St. Helens is this little dot right up here. So the most recent Yellowstone eruption is only the second largest. There it is. So here's St. Helens in terms of its volume from 1980, and then here is the most recent Yellowstone one here. So we're thinking about really, really big, explosive eruptions that would pretty much decimate North America. Yes. So I should say, when I was teaching in Boise, because of the weather patterns, Boise was upwind from Yellowstone. So I said, as long as you can tend your garden, you'll be okay. And that kind of settled people in Boise. Okay, whoops, let me back up. Yellowstone has quite a history from the last 16 or 17 million years. It is interpreted to be a hotspot where we have a stationary plume of magma or heat that is coming up through the crust, and as North America moves over that plume, it generates these super eruptions throughout the Snake River Plain of southern Idaho. And then the current location just north of us here from Jackson at Yellowstone Caldera. So there's been this history of super eruptions throughout the Snake River Plain over the last about 16, 17 million years. Okay. And as I mentioned, the ashes from these super eruptions can travel far and wide. So this figure here is just showing the extent of some of those ashes and where you can find them throughout North America. And as I mentioned, you can also find them in drill cores down in the Gulf of Mexico. Okay, so those are some super eruptions. And I said we want to look at how the magma chambers evolve prior to an eruption, and if that can give us any kind of indication of how the system works and how it builds up prior to a super eruption. So the mineral that I use to look at these magma chambers is called zircon. And zircon is basically a zirconium silicate. It has a very simple structure, which is shown on this diagram. It looks a lot more complicated than it actually is, but it is ubiquitous in these types of silicic systems. So it is there. It has very refractory properties, so it doesn't lose its viability as it is exposed on the surface to surface weathering or glaciation and things like that. So it holds its properties very well. It also accommodates very large ions. So the structure of this thing allows for, most importantly, uranium to fit into that structure. Okay? And we're going to use uranium lead dating to be able to kind of probe at some of our the zircons in here. So we can incorporate uranium into these things, which makes them very useful for that uranium lead dating. The other thing that I have up here, it has a high closure temperature, which means that once these things form, it's very hard to reset the age on them. So you have to heat them up a whole lot beyond their kind of lock-in temperature to be able to reset it. So when we do the dating on these, it's very, the dating becomes very accurate because you can't manipulate the system by external or other internal forces. Okay, so that's why we use zircon. And we are using zircon in this kind of new method that's called petrochronology. Okay, and up here I have some images. These are cathode luminescence images of Mesa Falls Tuff zircon, and you can see that there's some variability in them. We've got nice long grains, we have kind of short stubby ones, we have lighter areas and darker areas, and so we want to look at these grains to find out if they can tell us anything about the processes within the magmas prior to an eruption. Okay. So our first question about petrochronology, how do minerals record these radioisotopic ages, uranium lead ages, with respect to processes and phenomena? And we really answer this question through integrating the textural, okay, so are they long grains, are they short grains, are they dark grains, are they light grains? So looking at the textural information along with some of the geochemical information. So again, we're looking at the composition of these things and the ages of these things and trying to match it to the pictures of the grains that we can get. Okay. And then finally, we can inform our interpretations of correlation, causality, and rates of processes. And rates of processes are very important to geologists because we want to know how fast or how slow something like magma accumulation can occur to produce a super eruption. Okay? And that's one of the, hopefully one of the answers I will provide you with today, how long it takes to build one of these super eruptions. So I'm going to give you a brief background on our method of how we do this. And so let me just read this to you. It's a big alphabet soup, but I hope that I will explain all of this to you today. So it's a CL-guided tandem LA-ICP-MS and CA-ID TIMS analysis for our petrochronology. So I'll go through the method very briefly, and then give you examples of the Yellowstone system and how fast it takes for us to accumulate enough magma to produce a super eruption. Okay, so let's start very briefly with the method. The first one being our workflow. Back up here. Okay, I'll walk you through our workflow from taking a rock to getting our chemistry and our dates of these zircons. Okay, so we take our rock, we'll crush it down. From a crush or a powder, we can also make a microscope slide, a thin section of it, we do a textural analysis. From our crush or powder, we will use magnetics and density to separate out, what am I stepping
You
on?
want to step on that?
To separate out the grains of interest to us. And so I brought a little vial of some of our sanidine grains to show you what that looks like. From here, maybe? Okay. From here, we can look at mineral chemistry from our microscope slides. We can also send some of our crush and powder to a chemistry lab to look at the bulk rock chemistry of these. And we can also look at isotope geochemistry from that crush or powder. So from here, from our hand-picking and magnetic separation, we can also measure the ages, the argon ages of our sanidine grains, which is out through here. And then the next part, we can look at quartz grains. I mean, so we are like really taking everything from one of these samples and poking and prodding it to get as much information as we can about the magma system. And then finally, on the zircon side, I'm going to keep remembering it's over here. On the zircon side, we will image the zircon grains, and then we will, on those grains, get the chemistry of them, and then we will also date them. So it's quite a process. It takes several weeks to go through all of this. Your argon ages take about a year to get back from a lab, but the zircon stuff tends to be pretty intense lab work for about a week or 2 weeks before it's all said and done. Okay. Here's some of our equipment at Boise State. This is our SEM. This is what does our imaging of the grains. It looks a little bit like, the Star Trek Command Center with all of the knobs that you get to turn. This one, I think, is from like 1979. It still puts out great images. It was before they were designed to be operated by a computer. It's pretty old school, but works great. So all of our images come off of this old machine. After we make our images, we will then use a laser ablation system, and I'll talk about that here in a second. So there's a laser right through here that we can put our little samples in, fire the laser at them, and it gets all of our chemistry of those zircon. And then we use a TIMS machine, which looks like this. It's basically an atom counter, and this is what gives us our dates. Okay. All right, so imaging grains. So these are catholuminescence images, and basically what happens is the chemical changes in the zircon will reflect back different zones of color. And it's kind of like looking at tree rings, right? So if you look at some tree rings, you'll notice there are light bands and dark bands that represent fall or fall and winter versus spring and summer growth of the tree. Well, the same thing happens with zircon, where we've got, grains that have, make sure I push the right button, grains that have maybe a darker core like this one and surrounded by new growth around that zircon grain. And the difference in the color is representing changes of the magma composition. Okay, so it reflects back different grayscale values, right? Different brightnesses of grays and whites based on the chemistry of those zones. Yes.
How long is it? Those are really tiny. How long does it take any one zircon to form? With rings?
With rings, you're thinking on the order of millennia. Okay. Without rings, could be faster. Yeah. I'll show you how, I hope to give you an estimate of the entire range of composition and how long that takes for a super eruption today. So that's coming up. Yes, Sam?
So the rings are a reflection of the change of composition?
Yep. So in
secondary ions that go into it?
Yes. We use a CL detector attached to an SEM. So it's a scanning electron microscope, and we're firing electrons at it to make the brightness come up. Yep. So on zircon, areas that are really dark have very high uranium, and areas that are really bright have very low uranium. Okay. These aren't from Yellowstone, these are just some example zircon grades to show you that there is quite a bit of complexity in zircon from one sample, long grains, short stubby grains, etc. Okay. All right, so that's our imaging, and then we do the chemistry on these grains. So if I back up, you'll notice that there are some circles here, and this is where we've fired our laser to get the chemistry of those individual domains. So what we want to do for something like this is fire at the center and fire at the edge and see what the chemical difference is from the center of the tree ring to the end tree ring to see how the changes have occurred during the whole growth of that zircon. So we use this method called LAICPMS, which stands for laser ablation. So we're firing the laser at it, and then ICPMS is inductively coupled plasma mass spectrometry. Okay, and this is what's going to give us our compositions. This is some of our standard data, and I'll show you a bunch of chemistry plots for real data. But this is some of our standard data as an example. And the system that we have at Boise State is kind of like set it and forget it style. You can set up your experiment. It's going to run about 200 individual analyses, all automated. We can set it up to start at 10 p.m. and then you come in the next morning and it's done and you've got all your data there. It's really nice. You don't have to actually push any buttons or drive the laser around.
What's the size of the sample?
Excellent. The size of the sample?
Because last night was just that one grain.
Yep.
This sounds like it's more.
It is also just one grain. It is actually one location on one grain. So here, like with this guy, here's our scale bar of 100 microns. So this is maybe 200 microns. This might be 500 microns. Right. Our spot size is as small as 10 microns. So we're using our laser, here it is, ability to measure 10 micron spots. So you can really put a whole bunch of spots on one grain, and if you're thinking about the tree rings, you can go from core to the kind of middle to another middle domain all the way to the rim to really look at what the timing was of the growth and how that magma changed its chemistry during the growth.
Can you do a multiple spotting, like as soon as, I don't know how sophisticated the equipment is, but as soon as it finishes one spot, could go to another so that during that 10-hour time frame,
Yep.
you have a sequential and maybe 10 spots
Yep.
rather than one.
Yep, you can, I mean, if your zircon grains are huge, yeah, you can put as many spots on there as you can fit. Yeah, exactly. So some of the ones that I'll show you from the Yellowstone area have, I think the most we put on them were 3 spots. The other process or the kind of methodology we've developed is also to do lines. So you can back up here. So instead of just doing a spot, you fire your laser along the length of the zircon. And then we can also kind of flip them over and do a surface analysis. So that surface would represent the very last bit of growth before an eruption. So we'll also do surfaces. So we have all that data for all of these samples as well. It's quite a complex data set. But I think I'm only showing spot analyses today. Okay. We've got a wide mass range, so this means that we can measure, on the ICPMS, we can measure a variety of elements, everything from titanium all the way down to uranium and thorium and lead, everything in between. Titanium is really important because we can use titanium concentrations as a proxy for temperature. So in this plot that I have here, this is our temperature based on the amount of titanium that we have versus some other chemical parameter. Temperature is also really important because we are assuming that as a magma cools and crystallizes, it's going to be easier to erupt once it reaches this like critical point prior to eruption. So we want to see how much cooling has taken place and how much crystallization has taken place before we blast out 300 cubic kilometers of material. Okay. We can do simultaneous measurements, right? And then our greatest measurement or greatest challenge is on that titanium because the uncertainty tends to be a little bit higher, about 10% for very small concentrations. Okay, so in our standard data that we have over here, we can see a couple of them. This is just one big grouping. There doesn't seem to be a whole lot of trends in there. In FC1, you can see it kind of bends down this way, so temperature would decrease as thorium-yttrium ratio increases. This is OZ2, has almost no variability in its chemistry, even though it has variability in its temperature. So what we're doing with the chemistry is looking for compositional trends coupled to changes in temperature, changes in time. So we'll also get the uranium-lead dates on this. Okay, so the two types of plots that we're really going to look at are concentration ratios, or concentration versus ratio diagrams, and I just pushed the wrong button, here we go. Concentration versus ratio diagrams, where again you can see these trends, and these trends could signify differentiation or evolution of the magma chamber, or they could also represent mixing. Right? So if you put together black paint and white paint, you get gray paint in the middle. And so perhaps this is that same kind of trend where you have one end that is white paint, one end that is black paint, and you've made everything in between. So we can look at these types of trends to get at process. We can also look at ratio versus ratio diagrams to reveal some subpopulations. So in FC1 that we see the single trends through here, we see two kind of parallel trends in this niobium, uranium, and thorium yttrium plot. And so there's two populations kind of running parallel to each other. Again, this is just our standard data, and I'll show you all of this for the Yellowstone eruptions as well. So our goal with using laser ablation and CL imaging is, do the trends that we see in the chemistry correlate to our CL images? That is, do we see different things like high temperature to low temperature, higher uranium to lower uranium? Like what are the patterns that come out with the morphology? Okay, we want to make sure that we can match those. Can we match those? We don't know. So that's one of the things that we're going to look at. Okay, so we would expect increases in these types of trace elements as we cool from core to the rim. Okay, and I'll show you some examples of that. This is a pretty ideal zircon. I think this is from Mount St. Helens. It's an internet photo. It's not a Yellowstone one. Ours are not nearly as simple. I'll say that these are pretty simple here. Show you more complex ones. Okay, the last part of our alphabet soup is the CA-ID TIMS part. CA stands for chemical abrasion. So on these zircon grains that we've already imaged and that we've already poked and prodded for the chemistry, we now want to date them using uranium lead. So the first thing we need to do is remove any kind of damaged area. So this is what we call chemical abrasion. So we'll take out, we mostly use hydrofluoric acid for this, but within the grain, all of that uranium is decaying to lead, and it creates some internal weaknesses in that crystal structure. So we want to get rid of those weaknesses and get rid of any sort of damaged area in the grain. So CA, chemical abrasion. ID stands for isotope dilution, and this is basically adding a tracer solution to our analysis so that we can better count the atoms of uranium and lead. Okay, And then the TIMS is thermal ionization mass spectrometry, and this is the bigger machine that was counting the atoms of uranium and lead. And so from our count of atoms of uranium and lead, we can calculate an age for the grain. Okay? And we can also do this for individual spots. Okay, so we get our ages back for these, and we plot them up just kind of in a ranked age plot. So each of these grains here, Z2 would stand for Zircon-2. This 20 down here represents 20 spots on the grain. So here's an image after being lasered. Okay, and you can see it's been poked and prodded, right, number of times to get chemistry, all different areas. And so the age here is, 416 something. And we're going to do this on 10, 12, 14 grains, however many. And we're looking for repeatability. So we'll take a mean of those ages and their uncertainties to come up with an eruption age. Okay, so this is like almost everything you can think of to do to a single zircon grain, right? By this point, they're dissolved, they're completely gone, right? There's nothing left of them. So then we turn to another mineral, which is the stuff that I brought with me today, which is sanidine. And so we can use the potassium-argon system to date the sanidine. And really our goal is to look at, or is to ensure that the ages that we get for the zircon are the same ages that we get for the sanidine, okay? We want to make sure that there is a consistency between the two techniques. Okay, so that was our method, and so now I want to show you our results from applying this method to our Yellowstone samples. Okay, so again, here are some grains from zircon grains from the Mesa Falls Tuff. Each of these numbers represents where spots have been placed on those grains, so we're sampling the chemistry. And just, a first order analysis of this shows that there are multiple types of grains, okay? And so do the chemical patterns that we see, right, reflect the different types of morphologies in these grains. This is Mesa Falls Tuff. I'll talk about some other ones first. Okay. So here's just a kind of a general map of the caldera systems. In the area, the first caldera system produced the Huckleberry Ridge Tuff, which is the 2-million-year-old system. There's an outline of the known caldera location. The second caldera was produced the Mesa Falls Tuff, which you can find up Highway 20 as you're leaving Ashton over to Island Park. And then the most recent caldera out here is the Lava Creek, produced Lava Creek Tuff. This is where the active caldera is now. Along with these, so here are some pictures of outcrop. This is the Huckleberry Ridge Tuff. This is the base of the Huckleberry Ridge Tuff here, down at Meadow Creek, which is in eastern Idaho. And so Huckleberry all up through here. This is some of the Heisey volcanic field deposits just below it. These are about 4 million years old. And then right in between the two, you have a nice cobble conglomerate. I think the cobbles are Cretaceous age in between those. Okay, so there is Huckleberry Ridge Tuff. Mesa Falls Tuff looks like this on Highway 20. This is a piece that I brought with me. This is a matrix, and embedded in that matrix are little pumice fragments. This is my colleague Amanda Laub. She's holding some of the pumices that we've collected. You can see them in outcrop. They're these big kind of darker areas embedded into this matrix. So I have one of those pumices, two of those pumices here today. The really cool thing about working with pumice is that you can show your superhuman strength. So this is us on the side of the road, me holding a pumice, James, who's here with me, showing off his strength. And these are some students that I had out with me. And you can really just walk along the highway and pick up pumice blocks that have been weathered out of this cliff. Okay? It's really cool. I mean, you don't have to really work at all for the pumice. The great thing about working with pumice is that it's really easy to haul a whole bunch of it out of the field. So we did not take either of those with us. We take the small ones. Okay. Okay, so I've been talking about these different tuffs, but preceding and following the big super eruptions, you have those not so super eruptions, and in the case of the Huckleberry Ridge Tuff, it was preceded by the rhyolite of Snake River Butte, and then followed by some smaller eruptions known as Big Bend Ridge rhyolites, and there's some blurred lines between these two, which I talked about last night with the rhyolites that erupted right along the edges of the caldera, if they are pre or post, things like that. And then we have the Mesa Falls Tuff. Some of my colleagues are working on these guys up here. These are not my specialty at the moment, maybe in the future. Okay, so we've got our super eruptions here, and then we have our pre and post not so super eruptions on either side. And here's a map of this. So this is the caldera boundary for the Mesa Falls Tuff, the Henry Swart caldera, and this is Ashton sits right about here. Upper Mesa Falls is about here, and this is the Island Park Reservoir. So there's a handful of these smaller, not so super eruptions on the edges of the caldera, and these are about 1.9 million. These are about 1.5, and these are about 1.3. Okay, so do we see any evidence from the zircon that suggests that these not so super eruptions are contributing to the growth of the magma of the super eruptions, right? Are these little not so super eruptions, these smaller ones, like are they helping to feed the system, right, and build up this giant accumulated magma that then later erupts into a super eruption? It's one of the questions that we're trying to get at. So can we compare the not so super and the super stuff and see how the system is growing? We also want to look at how much crystallization is taking place prior to an eruption. And so we can model that, and I hope to show you some results today that really suggest this notion of cold storage, right? Oftentimes we want to think about the magma sitting below Yellowstone as just this like hot bubbling cauldron thing that's sitting there waiting to erupt. But I think the evidence shows that it's mostly solid for extended periods of time, and then small bits of that solid material will erupt. And then finally, how quickly can we assemble a super eruption? Okay, and I think this is a pretty exciting effort. Okay, so let's start with some zircon. Some morphology. This is Snake River Butte. This is that one eruption that is documented prior to the formation of that first Yellowstone caldera. And in the Snake River Butte, most of the grains look pretty similar. They have about the same gray tones or grayscales throughout. They're all nice and long. We've got one that might have a little bit of a darker, inherited core or something, but fairly uniform in their morphology. I'm going to add on to this our Huckleberry Ridge Tuff grains, and again, they all look to be fairly uniform. They all have about the same color. There are a handful of grains, like I'll point out this one that you can see. If I get over here, this moves faster. You can see that it's kind of truncated at the top, and then there's a growth over top of it towards the tip. You'll see another one of those here. But again, fairly uniform looking. Okay. And then here are Mesa Falls Tuff, and we start to get a little bit more complexity in the Mesa Falls Tuff. Really, really long grains, really short grains, grains that are brighter than others, and these ones that have these very dark cores in them. And the dark cores are going to come back to haunt us here in the next few minutes. Okay, so Snake River Butte, and then the two super eruptions, right, the zircon grains for those. Those smaller, not so super eruptions, yeah, not as pretty. Actually, they're prettier, but once you get these kind of complexities, it's harder to explain their growth patterns and what that growth pattern means for the chemistry. So when you look at these things, this is Moonshine Mountain Dome, right? This guy here. Is it easier if I just point? You see it? So the Moonshine Mountain Dome, I lost it again. Right, you have very, very bright grains. You've got grains that are very dark. You have grains that look like they've been chewed up and spit back out, right? Very complex over here. In the Green Canyon flow, dark core, you've got these really nice, this nice truncation, some smaller bands in it. And then this is the Tuff of Lyell Spring, in which you get what looks like multiple zircon growing together, okay? So these are very complicated, and the more complicated things get in their morphology, the harder it is to explain how those magmas are assembling. So I'll bring these back up from time to time, but I'm not going to focus on them because I don't even think I have a full grasp on what is happening. Okay, so when we think about the zircon chemistry with the morphology, some of the things that we can kind of predict would be we would expect that the core of our zircon is going to be hotter than the rims, okay, just because our magma is slowly cooling below the surface prior to eruption. We're also going to expect, okay, things like niobium to increase from the core to the rim. So niobium is a trace element that doesn't really get included into any mineral. So it's going to hang out in the magma as that magma crystallizes, and the zircon is just going to kind of record that, that trend as the crystal cools. And then finally, this is my favorite, this is europium. Europium is a very good indicator for how much the magma has crystallized prior to an eruption. So for europium, we're actually going to see the opposite pattern. We're going to go from high europium in the core to low europium in the rim. Okay, and this is going to be your common, like your a very generic theoretical approach to looking at a zircon from its core to its rim and how the chemistry of your magma should change. Okay, so this is what we expect, and this is what we see. Okay, this is data from the Mesa Falls. We have temperature, so hot temperatures to cold temperatures. Here is europium. High europium is on the right, low europium is on the left. And we've got this very nice correlated trend from, trying to do this behind my back. Did I find it? From high temperature, high europium to low temperature, low europium. And so the question is, does this correlate to the core to the rim? And the answer is yes. Okay. So in the Mesa Falls Tuff, we're seeing the trend that we expect to see in this kind of very generic theoretical approach to the chemistry. Okay, so across all of these, the good news is, and I didn't put the little trend lines on here, but the good news is these are all temperature versus europium, the same plot for the Snake River Butte, for the Huckleberry, and for Mesa Falls. And we see that same trend in all three of these, okay? That's great news. That means that all three systems are acting in exactly the same way, okay? There's the other plots that are up here are just supporting evidence for those. Here, this one is, this is niobium. And so again, we see high temperature to low temperature with low niobium to high niobium from core to rim. Okay, so the data matches our predictions, and this is true for the first cycle stuff, so the Snake River Butte, the post-Huckleberry eruptions, which are Blue Creek and headquarters flows, also for the Mesa Falls. Our really nice trend down through here is what we expect to see, and it's correlated from core to rim. Okay, so it's acting in a very predictable way. The stuff over here are results from those zircon grains that were really nasty looking, right? So they do not show the same pattern as the rest of the super-eruptions. Okay, again, more evidence that these things are really complex. This figure is showing, again, the core to rim trends that we see, and then now I've also put up some of those zircon images from the Huckleberry Ridge Tuff. In this case, this really nice one that I pointed out earlier, where you have all three colors. Okay, so the high temperature stuff, the medium temperature stuff, the low temperature stuff, and it's correlated to different locations within a single grain. Okay, so we're doing exactly what we were hoping to do and what we could predict, and the good news is that Huckleberry Ridge Tuff is showing us exactly what we predict. Okay, so when we look at Mesa Falls, right, we see that same quarter rim trend, but what's interesting are these black cores. So if you look at these grains, these black cores are green points, which correlate to green over here. Well, these are actually the coldest and the most lowest europium, okay? But it doesn't necessarily plot on all of the rim composition. So you expect everything in green to be on the rims, and it's not. Okay, so these black cores are going to be the kind of the next part of this talk, to think about what's up with these things, where did they form, and how did they form, and why are they so different. I'll tell you that their uranium concentrations are as high as 20,000 parts per million, which is almost 2%. Okay. So these things are really, really high in uranium, which makes them also really radioactive, not to the point of being in danger, but very good for analysis. Okay, so can we see some trends, some thermochemical trends between the super and not so super eruptions? And it's generally yes. Okay, so what we're seeing between the Mesa Falls and the Huckleberry Ridge Tuff are the same trends, and that they match with our predictions of how those things should behave. Okay. Yeah, that's the same thing I said, except for those eruptions that are more associated with the Mesa Falls Tuff look more complicated in their morphology, and guess what? Their chemistry is also more complicated. Okay, so let's go back to these black cores, and thinking about what they represent in terms of eruption and magma dynamics. So these black cores are quite pervasive throughout the Mesa Falls Tuff. Here are a whole bunch of samples of those, and you can see them here and here. And it's very hard to also get a spot on some of the rims of these because the cores get to be so big. Here's a really nice one that has just the smallest amount of rim material on it. Okay, so what we wanted to try to do, because these things had such high uranium, also really high niobium, can we try to model how much the magma had crystallized prior to eruption? Okay, so what does that look like? Well, first off, let me just say we sampled like 5 different pumice samples, so individual pumices that we were holding up in the air. So 5 different pumices, 2 of the more matrix-rich stuff, and all of them have these zircons with the black core. So that tells us that things were really well mixed. Okay, that the magma was really well mixed. It wasn't like we were getting a little bit of magma from over here and erupting them at the same time. Okay, so they make up, roughly 10% of all of the zircon analyses that we did. Okay, and so when we look at just something like europium, which remember that your high europium should be found in the core, low europium should be found in the rim, and niobium, which is the opposite pattern, we see that core analyses tend to be high, and then we get down to these dark cores, and they have very high niobium. Well, we can put a crystallization model onto that, and we can see that the normal quarter rim stuff can crystallize after about 5, 10, here's 40, 50%. So if we take our magma and start crystallizing it to about, get the initial 5 to 10% underway, we can start to make zircon. And then we can continue to crystallize that magma, grow zircon to about 50%. Okay, and our entire chemical trend is captured in that initial 50% of crystallization. Well, what's happening is that those black cores that have the very different chemistry are representing something like 90 to 95% crystallization. So that means you've taken this magma, right? And again, we're thinking of these big magmas that are sitting underground, so they're just bubbling and boiling away, right? But you've actually made that entire magma almost solid, okay? It's like now 90% solid, okay? And that's being represented by those dark cores. Okay, so this is for Mesa Falls Tuff. Here are those images again, right? So these dark cores are representing 90% solid. Well, that doesn't make sense, right? Like if this is solid, how is it going to erupt? Okay. So the next question that we had to ask was, well, if these dark cores are solid, what's the age of them? So then we started to, let me just back up. To Snake River Butte and Huckleberry Ridge Tuff, which we see the same pattern, right? So about 50% crystallinity prior to eruption, okay? So everything, again, looks the same here as it did with the other kind of chemistry. Okay, so can we model the degree of crystallinity prior to eruption? Well, it looks like we've got about 50% crystallinity that occurs before those super eruptions happen. The same looks for the smaller, not so super eruptions associated with it. These black cores look like they are almost solid, and so this is some of the evidence that we're using to support this idea of cold storage, which means that we're basically keeping a solid magma below the surface and then periodically extracting eruptible magma from it. And I'll come back to that here in a minute. So the Mesa Falls most likely tapped a previously crystallized material and then grew new stuff around it. And I'll show you some of that evidence here in a second, but then erupted at 50% crystallinity. Okay. So when did that earlier magma intrude? When did those cores crystallize is our next question. And this is, this was multiple years of like sitting there looking at these things being like, where did you come from, right? So it was, you're kind of seeing my progress of thought throughout working on these units over, about 8 years or so. Okay, so from knowing when those solid cores were formed, we can then also try to get a handle on how fast the super eruptions, the magmas, can accumulate before they erupt. And this is important because we want to know when the next one's coming, right? Okay, so going back to our ages of these things, and I presented these results last night with the Huckleberry Ridge Tuff. Has an argon age of about 2.08, 2.1, Snake River Butte about 2.14. So these are their argon dates. These are all of those uranium-lead zircon ages that we analyzed by the CA-ID TIMS. And we come up with about the same age, right? So if we look at Huckleberry Ridge Tuff, all of these things kind of overlap around 2.08, and these guys are clustering around 2.15, 16, something like that, okay? So the nice result here is that the argon ages and the zircon uranium lead ages are agreeing. Okay, so how does this correlate with the zircon morphology and the chemistry? Okay, well here is this grain that's 2.2, which is this point up here. And so notice that it has this core with this truncation around it. So this thing might be a little remnant of Snake River Butte that got picked up and carried along the way. These guys have the really cold chemistry, and they're pretty homogeneous looking, and they're the young ones. Okay. So again, a very nice correlation between the chemistry and the morphology, and we can see that the whole range of ages, okay, only represents about 40,000 years. So all of the chemical analyses that we have done, the models that we have done to it, and the dating suggests that you have all of this stuff happening in as little as about 40,000 years. When was our last eruption at Yellowstone? 74, right? So are we, in some period where we're just accumulating this magma now, right, over the last 70,000 years? Or is it a period of cold storage where everything's solid and we haven't made that new magma that can erupt again? So this is for Snake River Butte, Huckleberry Ridge Tuff. What's next? Mesa Falls, right? Okay, here's Mesa Falls data. I should have zoomed the scale in a little bit more, but our ages here are from about 1.4 to 1.3, 129, something like that. And this has an eruption age, according to the Argonne, of about 1.3. Plus or minus, let me just point out to you here, this is 500 years. So the dating techniques that we're using now can get our uncertainties down to hundreds of years when considering million-year-old eruptions. Okay, so thinking about the grains and how the grains correlate to the ages, some of these grains that show fairly simple-ish patterns, okay, are about 1.5. Those guys are sitting up here. The ones that are the youngest, okay, are about 1.3. So those guys are sitting down here. Well, here are those black cores. And those black cores are sitting somewhere in between. They're actually the really small dots that you see on here. Because they have such high uranium, we can do really high precision dating on them. So we know that these dark cores are older than the stuff that was formed right before eruption. So then the next thing we did was, I said, well, let me extract all of these dark cores and let's look at the distribution of them throughout our pumices. And these are probability distribution plots, and it's a little messy, but I hope I can talk you through it. So each of these is an individual pumice. And this is just a line, the open line over here shows us the distribution of the normal chemistry. And then the closed areas through here are showing you the peaks of ages for those dark cores. And what we find is that if you do some statistical analysis on these distributions, you come up with 4 different populations of ages for the dark cores. So we get our youngest population, right, which has normal chemistry, coincides with our argon date. So that works out great. But with these dark cores, we get about every, few thousand years, another spike in the number of dark cores that we're seeing within this 10% of zircon grains analyzed. So every 10,000-ish years, we're getting what I've interpreted as a little pulse of new magma that comes in and solidifies. It never erupts. And then another pulse comes in and solidifies and never erupts. And then finally, you get enough accumulation of those pulses and new magma that can erupt that the Mesa Falls magma has basically scavenged all of the new stuff, or all of that earlier existing stuff, and blasted it back out. Okay, so for me, I see each of these periods as times where new magma has come into the crust and never erupted. It's pretty important, right? It's pretty important to think about how we build the crust, the continental crust, and how these things are assembling. So, did I skip one back here? No. Okay, so I just zoom in to the top, and again, here's kind of what I was just saying. So these dark cores place some maximum constraint on how long it takes for these things to assemble. If our youngest population, which matches up with our argon age, is 1.30, and the next one with those dark cores is 131, 132, right? That's a maximum of about 10,000 years, 15,000 years. But this question, where's the record of this? Can we see anything on the surface that is related to these earlier pulses? And that brings us back to these crazy looking zircon grains, okay? So then we said, well, these things are nearby, you know, are these the same age as the Mesa Falls Tuff, and are they contributing and all this stuff? And the short answer is no. Right? These are not related chemically, texturally, or by age to anything we see in the Mesa Falls Tuff. Yeah, so if we had this record of volcanism associated with these, you know, pulses every few thousand years, it's been gone, right? It's not preserved. We don't see it in the area. So how quickly do these things assemble? Well, we can see our whole chemical trend in something like the Huckleberry Ridge Tuff preserved in about 40,000 years. In the Mesa Falls, okay, by using those grains that represent near solid conditions, we can determine a maximum differentiation time of about 10,000 years for the Mesa Falls Tuff. Okay, and there's no earlier record, or no record of those earlier pulses into it. Okay, so what does this mean for current Yellowstone? Well, hopefully we'll have 10,000 years of notice prior to the next super-eruption, right? But when thinking about how the past can help us understand where we are today in the cycles of volcanism out here, knowing that it's going to take about 10,000 years for this what we see as cold magma, right? Cold solidified rock to become liquid and then to start to crystallize again prior to eruption will take about 10,000 years, in my opinion. Some other scientists might tell you something different. So just some final thoughts on this, right? We have done a very comprehensive survey on these zircon crystals from individual pummices, from the super-eruptions, from these little tiny, smaller, not so super-eruptions, and really done everything we can on the grains to try to understand the complexities of these magma chambers. Okay. This question still kind of haunts me. So why does the Huckleberry Ridge Tuff lack those same dark cores that we see in the Mesa Falls? I don't know. I don't have an answer for that. But surely it had to happen, right? We surely needed to have some earlier periods of injection to accumulate all this magma. I don't know where it is. And then, right, the Yellowstone system is undoubtedly complex. One of the things that I like to think about is, you know, Yellowstone is unique, right? It's very unique to all of us. But is it globally unique in terms of its volcanic processes? Okay. Do we see the same type of differentiation patterns at other super-eruption sites around the world? And that is something that I think we are moving towards by taking this method that we've developed to image and do the chemistry and do the dating on it to really get at the systematics globally. With that, I just want to give some thanks to my collaborators, Mark Schmitz and Jim Crowley and Marion Lytle at Boise State University. Brian Jika is at the University of Wisconsin-Madison. He does all of our argon dating. If you're ever in the need for argon dating, this is the guy who will give you hundreds of years of uncertainty instead of thousands. Pete Lippert is this guy down in front. He is our paleomagnetist at the University of Utah. And then also my students at Westminster College have put in tireless hours on these units and helping us to understand the dynamic processes. This work is funded through National Science Foundation, so thanks to your tax dollars, I get to be here and share results of what I find is to be very exciting research. So with that, thank you and thanks for having me.
Thank you. All right.
This is at Mammoth Hot Springs, by the way.
Oh, yeah.
You got to take your students to Yellowstone. Yes, ma'am.
Has this same analysis been done on the earlier ones in the Snake River Basin, or is there thoughts and plans and hopes?
Yes. So I know some folks are working on the High C volcanic field. I know some folks are working down on the Kaimana core, which is south of Twin Falls. The stuff in between, like in Peekaboo, I don't think anybody is really working on that, or out at McDermott. This is, it's fairly time intensive to do these kind of analyses.
And money.
And expensive.
In our current situation.
Right. And so, yeah, people want to do it. I know that there are folks working on other aspects of the Yellowstone system as well, looking at oxygen isotopes in zircon, showing evidence that you've got these magma pulses that are coming in and they are interacting with hydrothermally altered waters, right? Hydrothermal waters to alter some of those zircons. So that's getting preserved in some of the oxygen as well.
And where else in the world is similar
Yeah.
to Yellowstone?
Well, I heard
Obviously, Hawaii is not.
I heard some of you are going to New Zealand. So New Zealand could be a very similar situation, which has super eruptions. Toba in Indonesia would be another one.
Oh, yeah.
There have been some throughout geologic time. The bubble image that I showed has the Wawa Springs on it, which is in southwestern Utah. And the deposits were so large that it was just only recently identified as a single unit. And so that was the biggest bubble on that diagram. So Eric Christensen at BYU is the one who really worked on that. Yeah. I think there are caldera systems in Chile that could be investigated. Yeah. Yeah. Yes, sir.
Do you ever run across zircons that are way older, say billion-year-old, or they don't survive the magma process?
That is a great question, right? So what we are showing evidence for is what has survived at the lower temperatures. Again, zircon is very refractory, but if you heat it high enough, can you remelt a zircon? So if you had something like from the Wyoming craton that is billions of years old, have you remelted it into this system? So far, we don't preserve anything that old, but it is a very much a possibility that they are there, we just don't see them. Yeah.
I just heard that the frequency of eruptions of Old Faithful are dependent almost solely on the size of the eruption prior.
Yes.
So if you assume regular or regular discharge or recharge, a small eruption would leave more for the next time.
Right. Right. Yeah. So we see this at Old Faithful, as you
So
point out.
there's an analog.
Yes, and so are we seeing the same thing, right, on the larger scales? Do these little not so super eruptions act as precursors to the penultimate super eruption? Yeah, no, that's a great analogy. I'll take the one in front.
Last night you talked about the hot spot that had moved.
Yep.
What about if there's correlation that, like all the swarming earthquakes that happen in Yellowstone, do you think that can be predictive in some way?
Yeah, so we saw this with Kilauea just a couple weeks ago, where the number and strength of and depth of the earthquakes became shallower, they became more frequent, and larger earthquakes, which signified magma starting to move. And so the same thing would happen in Yellowstone if the volcano was to wake up, right? We would hopefully see the same thing. We haven't been around for one of these. We haven't been here. We weren't here 74,000 years ago to watch the activity happen and unfold. And so we were assuming that, one of those earthquake swarms would act as some sort of warning for us. The 1959 Hebgen Lake swarm associated with that, but then there was no eruption, right? So something was moving, but it didn't lead to any kind of eruption. Yeah. So hopefully we'll have those kinds of signals.
So we have another 10,000 years to wait then.
Well, yeah, I mean, right. Yeah. Yes, sir.
Can you help me understand something a little simpler here?
Sure.
About the zircon crystal formation. Do I understand these zircon crystals are forming from a magma in a solution type of crystallization, which is far below the melting temperature of the zircon.
Yes.
Okay, and is that below the temperature, okay, and so they can redissolve too if the magma gets hotter.
Right.
Is this below, is the magma below the closure temperature that you spoke of for recording the crystallization?
Yeah, I think the closure temperature on a zircon is something like 950 degrees. And so, C, yeah. And so the eruption temperatures on these things are closer to about like 700. So the benefit of using zircon is that it's really, once you form it at 950 degrees, you got to do a whole lot of heating to bring that magma back up above 950 for it to redissolve. And it could be in some of those Tuff of Lyle Spring, those really complicated ones that I said it looked like it got chewed up. Maybe that has some redissolved zircon along with it. But yeah, we're assuming all of this is taking place below the closure temperature of the zircon. So it's actually recording and it's not being an open system between the solid grain and the surrounding magma. Does that answer? Yeah. Yes.
The ones that have the dark cores, are those temperature dependent and or whatever's in the solution dependent?
Yes. So the dark cores tend to be the coldest. So they're somewhere around 650 to 700 C. So they are temperature dependent, which I think again points to being nearly solid.
But you have to have something in the solution to produce the chemistry.
Right. So the way that these trace elements work is when you think about a crystal structure, certain elements can plug into that crystal structure based on their size and their charge of the element. So in the case of zircon, uranium likes to fit in for the zirconium because it's about the same size and has about the same charge. So it's really easy for us to put a uranium atom in where a zirconium atom would be. But when you think about the other minerals in the system, quartz and feldspar, uranium doesn't fit into those. So as you're cooling and solidifying your magma, you're leaving behind all of this uranium that can then get taken up in something like zircon because it doesn't want to go into something
But
like
the
a
uranium
quartz.
is not universally there, but it's hanging out.
Yeah.
It just
Yep.
depends on what it can plug into.
Right, exactly. And so if you're not making anything that the uranium can go into, it's just going to keep hanging out. And it's going to concentrate more and more and more
In the matrix,
in the surrounding magma. Yeah.
which is a matrix when it solidifies.
Yes. And I often try to, when teaching my students about concentrations, right? I often use, the analogy of whiskey. So you can make a cocktail with 1 ounce of whiskey and 12 ounces of Coke, or you can make a cocktail with 2 ounces of whiskey and 12 ounces of Coke. And so one of them is more concentrated than the other. And that's exactly what we see within the magmas, is that we tend to concentrate, right, more and more the uranium as we crystallize it and can take out everything except for the uranium. They like thinking about whiskey because they're not old enough to drink it. Yes, ma'am.
So the other elements, the European, Namibian,
Yep.
titanium, are they in a constant, or are there changes in the composition of the magma?
Yeah.
Of-
So they are not constant. They are going to change depending on the amount of material available, and it gets back to this concentration thing. So as you start to solidify your magma, if you start with 100% liquid, right, and you start to make solids, crystals within that liquid, you're then going to reduce the amount of liquid, but you're going to increase the amount of the concentration of something like niobium and
Which doesn't go into as
which
readily
doesn't
as
exactly.
uranium.
Yep.
But, okay, so where does the magma come from?
Where does the magma come from? Melting of something solid.
And is that uniform
That-
or not uniform?
So it depends on your tectonic location. At mid-ocean ridges, we create magma through what we call decompression melting. So as you pull apart at the mid-ocean ridges, it releases the pressure on the underlying rock. That release in pressure causes the phase change from solid rock, solid mantle, to liquid magma. Here at Yellowstone, the idea is that there is an upwelling plume of heat, right? So this mantle plume or a hot spot. So it's the heat that is coming up through the mantle and it's helping to melt the crust as well. And so it's melting the solid crust. One thing that I think that we often say, oh, you know, there's magma under there and it's mantle, but that stuff is solid, right? We'd be in real trouble if it was all liquid. We wouldn't be able to sit on it.
But it varies.
But it varies.
location.
And then it's a different
elemental.
melting regime in places like the Cascades, where you have subduction, where plates are coming together. Yeah, drives a different type of melting. Yeah. Great questions. Yes, ma'am.
On the one where you said they were rings, what is the composition of the rings? Because if the core is this solid, what is
Yeah.
around it? Is it just the same thing, but in a lesser, not solution, but percentage?
Yeah, well, so that ring is also going to be a solid, but it's representing the change of a magma after crystallization of other stuff. So if you think about the magma that is constantly changing its composition as we are crystallizing, those rings represent moments in time, a snapshot of that magma, if you will, of the chemistry of that magma at the time that that ring formed. If we could do, say, 1 micron spot sizes, we might be able to get at individual rings. But even with a 10 micron, I think most of these spots are 25 micron, you might be averaging 4 or 5 different rings together for their chemistry. Yeah. Yeah.
Why did you choose, zircon? It's probably been proven to be the best material
Yeah.
to study, but why is it the best?
Because it's so pervasive, you find it in abundance. And I should say that our zircons are whoppers in the terms of zircon. They're big, and by big I mean 200 to 300 micron, right? They're nice and long. Many zircons are only a few tens of microns long. So in the Yellowstone system, we have gigantic zircons, which makes it really easy to work with. They also hold their age very well. If they are, out exposed on the surface, they don't weather away very easily. And then it's very hard to reset that clock. You really have to heat them up to reset the clocks on the dates. Yeah. So they're good in a variety of ways because they're so sturdy.
So you have something in a liquid state and the zircons are beginning to form.
Mm-hmm.
So 3 inches away, some other zircon is beginning to form. Do they change in how they look and how they form? Or are we looking at twins in a big bunch?
Or do we know?
If they are nucleating at the same time, they should all be homogeneous. I think the ideal situation would be if you're adding a new growth ring to 2 zircon at the same time, those growth rings would be homogeneous as well, assuming that you had a very well mixed solution.
3 inches away, is that well mixed?
Yes.
So when you break into one of these things, if you get one zircon, is that because it's going to be like 10 others around it? Or it seems to me that you're looking at very different snowflakes.
Yes. When we process the rocks, so in this little vial that I have here, these are sanidine, right? So I've just taken one of these pumices like this, just taken this thing, crushed it down and made a little vial. And then we're gonna send off maybe 100 of these to be analyzed. So in the pumice, right, we're doing the same thing with the zircon. We're gonna crush it down and basically select at random 100 grains. So they could be 3 inches away, they could be 3 millimeters away, they could, and so we're sampling that at random in hopes to get the best distribution of the entire system. Yeah.
Okay, you just mentioned looking at zircons which are fairly close.
Yes.
Is there any difference between the zircons in the same volcanic flow from further distances apart?
I haven't done an analysis of, like on some of these smaller systems where like the Bishop Mountain flow, from the near vent to, distal. I haven't done that kind of analysis, but with something like the Mesa Falls Tuff, because we just sampled individual pumice blocks kind of at random, anything that fell out was on the ground, right? And we get the same distribution of like the zircon types throughout all of those pumices. I think that's a pretty good indicator that things are being very well mixed and that you're not getting such differences.
Well, if you knew
within
where
the
the
magma.
vent was, and you could sample close to the vent, and
Yes.
far away from it, assuming the farther away lava is erupted earlier.
If they were two different eruption pulses or
No,
something.
just one eruption.
One eruption.
But if you knew where the vent was,
Uh-huh,
you could take a sample there,
yep.
which would be the
Oh,
latest.
the end part of the eruption.
Yeah.
Yeah.
Is there any, have you ever looked at
Haven't looked at that,
that?
no.
There's too much to do.
Yeah,
You have to find
yeah. There's, clearly you can see we try a variety of things and,
Tiffany can
Every-
stay and talk with you about the rocks for
Oh,
a
yeah.
little bit.
thank you.
Thank you very much.
John's got to run.
I've got to